Okay, so the last lecture of this quarter, we're going to talk about, continue to talk about a little bit about reinforcement learning, finishing up some of the discussions about the policy gradient. And then we're going to introduce a new algorithm called PPO, which is an extension of the policy gradient, which is one of the most popular algorithm people are using for training large language models. And then we'll move on to how to use reinforcement learning for large language models for this kind of like verifiable, like how do you train long COT, how do you train models to have the long reasoning capabilities with all the thinking tokens. So that's pretty much the agenda for today. So I guess let's finish up some of the discussions about reinforcement last week. So recall that we are talking about this so-called policy gradient algorithm. And we did a lot of derivations in the last lecture, last Wednesday. And this was the starting point we had, right? So we have a loss function, or reward function, which is the total return. You have some discount factor, which is not that important. You sum up the return at all time step t. And then you take expectation over the trajectories, right? And where the actions are sampled from the policy theta. So, and recall that the challenge here is that this thing, inside expectation, there's no dependency on theta whatsoever. So the dependency on theta, on the parameter theta, is in the sampling probabilities you are sampling the actions from. So so the dependency is kind of like in a weird space, so that you cannot just swap the gradient with the expectation, because then you ignore all of these dependencies. If you just take a gradient operator and you swap the expectation with the gradient, this whole thing doesn't have any gradient with respect to theta. So that's why we have to use this so-called policy gradient estimator to estimate the gradient in a different way. And we did a lot of derivation, and we found out that the gradient of the return is equal to this thing, which is, so basically the key term here is that you have the reward, which is this is the same as the total reward. And this is the probability of the whole trajectory, you see, right? So, actually the conditional probability of the actions of the whole trajectory, right? So basically you take the sum, oh, my bad. This is gradient of the log. So maybe if you, okay, whether you put the gradient here or here, it doesn't really matter. So the sum of the log here is the log probability of the whole trajectory. So, and you take a gradient with respect to theta. So the last time we didn't have a lot of discussions about how to intuitively understand this. Last time we derived this from the equations. But if you just stare at this equation, it actually makes some sense, right? Basically what this is saying is that you are always maximizing the return, which means that you are maximizing the log probability of the actions you sampled. But you maximize it with different weighting. So if the reward is high, you're going to have a higher weighting for the log likelihood of this trajectory. If the reward is low, let's say the reward is 0, then your weighting is 0. So basically you are not maximizing those the log likelihood of those trajectories with reward 0. So basically this is the weighting term that controls how much you maximize the likelihood of each of the trajectory. And if it's a good trajectory, you have more weights, otherwise you have lower weights. So that's essentially what the policy gradient is trying to do. And now let's spend a little bit of effort to simplify this even further, because actually this is still somewhat kind of like unnecessarily complicated. We already simplified quite a bit, and we can still simplify more. So one of the key things that you use to simplify is that actually, oh, this doesn't work again. So what happens is that there's a very important quantity that we should realize, which is that if you sample an action AT from this pi theta, from this policy, and you look at the expectation of the gradient of the log of the probability. Right, so AT is a random variable. You sample it from this policy. And then you look at the log probability under the same policy, and you take the gradient. So this is a numerical number, right? So, and you take the gradient of this function with respect to A, right, with respect to theta, and you take the expectation. This is 0. So basically, it's saying that, in some sense, it's kind of like the gradient of, So in some sense, this is the abstract way to think about this is that if you have a random variable x, it's sampled from some distribution p theta, let's say, then the expectation of the log probability of this is always 0. And the reason is actually very simple. The reason is that if you just, this is a kind of a claim. And the reason is very simple. You just you expand this. You can expand this by writing it as an integration. So expectation of x is p theta x, right? So this is what expectation becomes. And then the gradient of log, maybe let's just write it down first. And dx. And then this is equals to, let's take the gradient. Right, gradient of the log is the gradient of the what's inside divided by the, this is like you are using the fact that log t, the derivative of log t is equals to 1 over t, right? So I'm using chain rule here. So and then these two terms got cancelled, so you get integration of the gradient of p theta x dx. And this is the, you can swap the integration with the gradient, you get, maybe let's stress that every derivative is with respect to the parameter theta. So nabla theta integration of p theta x dx, which is equals to nabla theta of 1, right? Because the integration of a probability distribution is always 1. So basically, if you don't have any weighting here, right? So here is this. What does this mean? This means that there's no weighting. You see, you just take the. If you compare this with this in some sense, right? Here you have the weighting for the different probabilities, right? For different actions, you have different weighting. If you don't have any weighting, then your gradient will be 0, which makes sense, right? Like if you don't have any sense about which action is good, which action is bad, you just take the policy gradient, you should have 0 gradient because no action is good or bad whatsoever, right? So, and the fundamental reason is just this, right? So like if you take the gradient of the log, there's no preferences in some sense because there's no, in some sense, reward function that they weight to. So that's a basic fact, right? If you have no weighting, then it's going to be 0. And now you can use this to simplify this a little bit more for the following reason. The reason is that some of the dependencies are considered as constant. So basically, if you think about this, if you multiply a constant here, that only depends on st, it wouldn't change anything, right? Multiply any constant that doesn't have any dependency on at wouldn't change your equation, right? You can multiply any constant here, it's still 0, as long as the c doesn't have any interference with at, it's not a function of at. So we're going to use that fact. So what does that mean is that if you look at this equation, and you can rewrite this into, you can have this for 2 parts. So the trajectory is somewhere from pi theta, and then maybe let's first move this sum all sides so that we can deal with each of the terms independently. So let's say you have a sum over t from 0 to t minus 1, expectation, gradient of log pi theta at st. And now let's use a different variable for the iterate here. Let's say use t prime is 0 from 0 to t minus 1, gamma t r st at. So this is nothing but just I'm kind of like putting one of the sum outside with this. It's just I'm not using anything yet. And then you can decompose this term into 2 parts. One part is that those t prime that is less than t. This t prime, sorry, t prime, at prime. And there's another part, so this thing, where the t prime is bigger than t. R as t prime, t prime. Okay, I guess this is t prime as well. So, and for the part that is bigger than t, I cannot do anything. Let's probably just denote this. Let's give a notation. Let's call this r larger than t, just as a simplification. What I'm going to deal with is that the part that is smaller than t. And I'm going to claim that it's 0. So the claim is that expectation of this log gradient of the likelihood times the part that is smaller than t. I guess I'm missing some prime here. Yeah. And why? The reason is very simple, actually, because if you think about AT has nothing to do with those things that happens before the time step t. So basically, the randomness in AT, all of these random variables are constant from the AT's perspective in some sense, because all the t prime happens before st even. Right? Once you see st, you actually all the history is forgetting. You don't have to care about history. The history is really a constant. So in some sense, mathematically, it really just means that you can take this expectation in two batch. You can first look at the randomness before time t. You can look at the randomness of like, let's say S0, A0 up to ST minus 1, AT minus 1, and ST. So you look at all of these random variables. And then you condition on these random variables and do another expectation over AT. So the next thing is going to be over AT. The randomness is going to be over AT. And you have gradient log pi AT given ST. And then times this thing. Yeah, and then in the inner expectation, you have already conditioned on S0 up to ST, right? S0 A0. You have right. So you have this nested expectation. This is a law of total expectation, right? In some sense, you are fixing these random variables. You are looking at the conditional expectation only over the randomness of AT, and then you take expectation over the things you have that happens in the past. So, and this is just law of total expectation. And what happens here is that if you look at this, then this part, after you condition all the history, this is a constant. You can move it outside of the expectation, right? So this inner expectation is the same as you treat this as a constant, because it's indeed a constant after you conditioning on those things, right? So conditional S0 up to ST times a constant here, right? So, and now here, because of the Markov property, so this term is here, so that I don't have to copy it. Because of the Markov property, condition on S0 versus condition on the whole history is the same as conditioning on only ST. So this is the same as conditional ST, right? So you are only looking at the randomness of AT, and that is 0, as we have discussed. Because if A is from ST and you take the gradient of the log of the pi, then it's 0. So that's why this is 0. And there's a constant here, which is going to be multiplied here and here, but you multiply 0 with a constant, it's still 0. So what's inside this expectation is just literally 0, and then you take expectation of 0 is still 0. So the whole thing will just evaluate to 0 eventually. Does this make sense? So in some sense, intuitively saying that, the weighting here is really just a constant because it's about the past, right? You can only, the past reward, there's nothing you can change. You should only weight your probability based on the reward you can change. Whatever you cannot change, shouldn't affect your decision, right? So that's why eventually this gradient of the, so with all of this calculation, you can write this as the expectation of times the reward to times the component that is here, which is not cancelled out. And let's call this, R larger than T. Often people call this reward to go. This is the reward that in the future that you have that you can affect. And this is the definition is just that term, right? Is all the future steps, the reward in the future steps. So basically, you weight the log likelihood based on what is the chance, what is the reward for the future steps. Any questions so far? Okay, so and now we're going to use this trick again to make it a little bit more complicated, but actually it's useful. So we realize that you can, I think the whole calculation here, the gist is that you can add any constant here that is not a function of AT, right? So basically the gist here is that, like I already said in some sense, right? So expectation of, like basically you can add anything here which is not a function of AT, right? Suppose it's only a function of ST, it's okay. If you get any constant that is only depends on ST but not anything after T, then it's okay. So basically it means that even you add another term here, as long as it's let's say, suppose you add another term, let's say you subtract some term, adding and subtracting is the same thing, that is only a function of ST, but not a function of any future states or actions, then it's still equal to 0, because this is a constant in this calculation. And the reason why people, and this is often called baseline, the reason to introduce this is to reduce the variance in the estimating the R's. So basically, whether you have this term or not this term, in expectation they are the same. But empirically, you cannot never estimate expectation exactly. You have to sample some trajectories, right? So, for example, if you, maybe let me give you an example. For example, if your reward is always between, say, 10 and 11. So the lowest reward is 10 and the highest reward is 11. Then if you use this, then it's kind of like this R will be always between 10 and 11. But if you subtract something to make it into the range between 0 and 1, it's kind of like making the variance smaller in some sense. For example, if the reward is always between 10 and 11, then you should subtract probably 10.5, so that the adjusted reward in some sense is between minus 0.5 and 0.5, something like that. So, and actually in reality these days people do adjust it something like this. You try to estimate the average reward to go in some sense, and you subtract that so that you can have a more kind of like balanced reward.
How would you calculate baseline?
So, in some sense it's just, the exact reason is not kind of like, there's no guarantees that it depends on how you subtract. Yeah. The reason is just that because you have fundamentally have another knob to turn, right? You always find something that can subtract it, right? So because in some sense the thing is you want to correlate this with this in some sense, so that how do I explain in an intuitive term? Like this is kind of like the classical control variable kind of stuff. Like you have a random variable, you want to reduce the variance, you find something that correlates with it, but it has the mean 0, and then you can subtract it. So basically, eventually this and this will be correlated, and you can, but this one correlated in the sense that if you consider all the randomness, they are correlated, and then you subtract that part, and then you can make the variance smaller. Does that answer the question? Maybe.
Would just be like 10.5 since it's constant, so
yes, if you just only subtract 10.5, no, yes. But the thing is the following. So maybe like, okay, yes, I think you are right. So my example is a little bit too oversimplistic. So if you just subtract a constant, it doesn't help anything. But you have to subtract a constant that depends on the ST. So basically, for example, for one ST, your R is between 10 and 11. And for the other ST, your R is between 0 and 1. And you're allowed to subtract 10.5 for the first one and subtract 0.5 for the second one. So that's why everything is on the same scale. Does it make some sense? So if you don't subtract, then for one of the trajectory, you are multiplying 10 or 11 here. And for another trajectory, you are multiplying 0 or 1 there, right? And now if you subtract something that can depends on the past, then you can kind of normalize all of this into the same range in some sense. Yeah.
I was just reading through that math, like there, the expectation term we have 2 terms, and the first term that you've established as 0. I'm just thinking like E, expectation of A to B is not necessarily expectation of A to expectation of B. Right?
So in which case? Like which line? This line?
Yeah, so like you basically said that the first part there, the expectation of that thing is going to be...
The first part of this is 0. The expectation of this is 0, yes.
Right, yes. And that means that the expectation is, like you just took out the expectation term for that first part and then multiplied with the expectation term for the second part. So it's like E of expectation.
No, I'm not. Okay, yes, that's a good point. So I'm not... So here, I'm not using the fact that this expectation of A times B is equal to expectation of A times expectation of B. That's not true, actually.
Yeah,
right? So I'm not saying that this is the case. So this is not what I'm doing. What I'm doing is that in my case, B is a constant. So B is literally a constant because I've already conditioning everything in the past. So this B term is really just a constant. So that's why I can take it out. Yeah, so I think actually regarding your question, I think I had a heuristic examples, in my lecture notes. I'm trying to see whether that's a good. I think that's kind of like similar to this. So basically, maybe one way to think about it is that suppose you have one trajectory, you have one state st, and the different actions will give you reward either 10 or 11, right? So in some sense, if you only use the reward, actually it's kind of interesting. So you are like the reward 10, suppose this action is giving you reward 10, this action giving you 11. And 10 is the minimum. So actually, in some sense, you should penalize the one with reward 10, right? But actually, in this case, if you don't adjust it, it's actually, on the surface, it's actually reinforcing both the two actions, either with 10 and 11. The only difference is that you are reinforcing the good actions with a stronger emphasis, and you are reinforcing the weaker actions with a lesser stronger emphasis. But why you should do that? Maybe you should just be more explicit, just to readjust it so that this is a negative example, this is a positive example in some sense. Right? In expectation, they're the same, because in expectation, only the relative difference is this matters. But in reality, it's more direct if you penalize this action in some sense. Does that make sense? Okay, sounds good. So that's everything about policy gradient. And now let's talk about the so-called PPO, which is a variant of this. So, and it's very kind of like still in some sense exactly why it works and in what cases it works. It's still kind of a mystery in some sense especially from a theoretical level. And there are so many different explanations. I thought about this for quite a while, and I don't think none of the justifications is really kind of like very convincing to me in some sense. So what I'm doing is I'm repeating some of the existing justifications with some of my own kind of like tweak in some sense. But just keep in mind, none of this is really very strong justification for this algorithm, and it's also not perfect. You'll see, like in the very last 20 minutes, we're going to find all kinds of ways to fix it in some way, and the fix is not perfect. And so basically, stability for post-training seems to be generally a big issue in general. It requires some magic, to make them stable enough. And I don't think we have a consensus on what's the best way to do that yet, especially in the open source community. Maybe the frontier labs know how to do it, but in the open source community, I don't think we reach a consensus on how to stabilize it very well. Anyway, so how do we start? So we can start from, let's say, here, right? So this is our starting point. So, sorry. PPO, no, PPO doesn't stand for, PPO is proximal, policy optimization, something like that. The name, I don't even remember I don't exactly remember. What's the first P? Proximal, I think. Yeah. Wait, is it really? Yeah. Anyway, but the word doesn't matter that much, I think. Yeah. Okay, so I think the idea here is the following. So sorry, let me just get my okay, so maybe let's start from here. So recall that this loss function is something like this, right? So it's like this trajectory come from pi theta, let's say gamma to the power t r s t a t. So if you take gradient, maybe one thing I should, maybe before talking about PPO, let's try to summarize the algorithm here. So the algorithm is that every policy gradient algorithm has this structure, right? So you first sample the trajectories from the policy. Maybe you sample many of them. So one trajectory or maybe many trajectories. Let me be a little bit, so let's say many trajectories. From the policy pi theta. And then you estimate nabla eta theta. You estimate the gradient with respect to theta. And then you do the parameter update. The parameter update, you say theta is updated to be like theta. Here you plus some learning rate alpha times the nabla of eta theta, something like this. So, and when you say estimate, the nabla, I mean I'm using this estimator to estimate. And what that means like I'm replacing the expectation by the empirical sample mean, right? So you have many trajectories like this. You take probably 128 trajectories, and you take the empirical mean as opposed to the full expectation. And the issue with this kind of algorithm is that it's so-called on policy in the sense that every time you update your parameter, you are so this kind of algorithm is called on policy because when you are updating the parameter is the most recent parameter that you use to sample the trajectory. So you are sampling from theta, right? From theta, and then you take the gradient at theta, and then you update theta. So, for example, what if you want to update 2 times? Suppose you want to say, I'm going to take 2 gradient descent steps. I take 1 step and I take another step. It's not allowed, strictly speaking, because the second step, if you want to take another step, you have to resample to estimate your nabla theta again. So because this estimator requires that this trajectory to sample from the policy p theta. You have to sample from the current theta to estimate the gradient at theta. You cannot take another trajectory from a different distribution. So that's the main challenge. So it has to be on policy because this estimator requires you are sampling from the current theta you are at. So that means you cannot reuse the samples. Right? Like if you take one trajectory, you only use it once for gradient descent, and then the sample is of no use anymore at all. So, and PPO is trying to kind of deal with this kind of sampling issue by importance sampling. So basically it's trying to reuse some of the trajectories you sampled from an old policy and still to estimate the gradient at the current policy. Or still estimate the gradient or the reward function at the current policy. So basically, the ideal thing, if the ideal thing is I want to replace this by, for example, something like this, a pi old, so that I can use the old policy, the trajectory from the old policy to sample. But if you just if you just do this, then it doesn't make sense, right? Because if you just do this, then you are not actually estimating the eta theta, you are estimating exactly eta theta old. so that doesn't make sense. So you have to somehow correct for the differences between these two. And the best way to correct, the simplest way to correct is the following. You say, I'm going to do some important sampling, right? So I sample here from pi old, and then I add some important sampling here. I add some kind of like a important sampling term here to correct for the distribution differences. So here the subtlety comes from that, how do you correct for this? Because technically this is a trajectory. This is kind of like the differences is the whole trajectory probability is different. So the first thing that PPO does is that, okay, let's try to at least correct for the action part. And at least that's something we can do, right? So basically the idea is that you say, let's first decompose this into two parts. One part is that the state is, sampling from pi theta, and then the action is sampling from pi theta given the state, right? So you first have this, decompose these two things. And then you say, at least I can do important sampling for this part, even though I don't know how to deal with it for this part. So I just say, you estimate this, I think this is actually equality, right? So you say, if ST come from the new policy, and then I do an important sampling where I change the AT to sample from the old, and then I take an important sampling to correct for the differences. You say you add pi theta AT given ST divided by pi theta old AT given ST, and then R ST AT. So something like this. So that's the first order bet you can do. So basically you correct for the action distribution, but you don't correct for the state distribution.
The policy going action from state.
Yes. So this means that yes. So what does this mean? This means that you actually, what does this really mean? It means that you sample the actions from the pi theta, and then you sample the state as a result of that.
Okay, I see.
So that's a typical way people write this kind of notations. I know it's sometimes people just say S come from this pi. I think they even have a notation for this, like say the distribution of the states and the pi theta. That's the more formal way to write it. But what it really means is just that you take the whole trajectory, sampling from pi theta. The action is sampling from pi theta, and then you keep the state part in some sense. And then you recorrect for the action part locally. So basically, this whole thing is sampling from pi theta, but locally you correct for the action. Yeah. So and then you can say let's okay. So now the problem is that you didn't correct for this part, right? But you just try to say, oh, I don't care. Like I cannot, there's no way I know how to correct for this part. I just use the pi theta old in practice, and then I try to kind of like just in some sense use pi theta old for this, which is a big approximation, and this part you try to correct. That's kind of like the main idea.
In the last step there, you the fraction there, the pi theta and pi theta old. This fraction, what does that represent? The gamma term?
Oh, no, it's not. Oh, sorry, there's still a gamma term. I guess just in natural language cases, like the gamma is 1, so that's why I always forget about it. But like this is trying to, so this will cancel for this, right? So this term, if you think about the expectation, there is a probability of the pi out, which will cancel with this. That's how you do the important sampling.
When if it cancels out, then like we should not be doing that. we should not be left with anything, right? Like,
yeah, so it's kind of like fundamental what he's doing is the following. Suppose you have x from p theta, and then there's a function of fx, I say, something like this. And how to do important sampling, you say this is expectation p theta x fx dx. Sorry, this is the integration of this. And then you say I'm going to introduce a q, and then I have p theta x divided by q theta x dx. And then you put this part in the expectation. You say expectation x come from q theta x, q theta, and I'm left with the ratio between q and p. And right, so I missed the fx somewhere. So fx dx, and this is fx, and this is the very analogous to this, right? So this is p, this is q, and this is q, right? So okay, good. And I think maybe in the interest of time, I'm gonna hand wave a little bit. You also can kind of like take gradients of this. So if you take gradients, you can actually how do I hand wave a little bit? So So I think what people often do is that people often subtract the baseline here, so that you have an advantage function. So, so you can kind of like so I guess with some kind of like a little bit kind of like hand wavy thing, you can also subtract the baseline to replace the reward by some kind of like advantage function. Advantage function, which we didn't really formally define, but you can think of as something like the reward to go minus some kind of baseline, something like this. Right, so this is like a baseline, and this is the reward to go. So, and let's call this something like a hat t. So you can do some derivation so that you can make this kind of something like this. So S from pi theta, and then expectation AT from pi old ST, and then you have this ratio AT given ST and pi old AT given ST times this advantage function. And the advantage function is really just saying that if it's positive, so of some AT and ST is positive, it means that AT is a good action. And this advantage is negative, it means it's a bad action. Because it's kind of like worse than a baseline, so it's a bad action. Okay, so basically that's the first, so that's kind of like the approximation. And then you try to approximate this, I guess as I said, you approximate this by pi old. So you say, let's not care about how I sample from the state. So I change this to pi old. Okay, so now, in some sense, it's kind of like in a reasonably good form. But now the catch is that this ratio sometimes is too big or too small, so that it creates some trouble. So for example, what if the ratio, this ratio, I think often people call this ratio little r, I guess this little RT. So if this ratio is, let's think about this ratio, right? If the ratio is big, what does it mean? If the ratio is big, it means that the action is, okay, so I guess it depends on whether the A hat, so there's actually 4 cases here. So if A hat is big, and the ratio is, let's say, much less than 1. So what does that mean? That means that A hat, the advantage is good, means that this action is actually a good action. So we know the reward compared to the baseline is positive. So the action is a good action. And it's a good action, and also under the current policy, it has higher probability than the old policy. So in some sense, that's already a good case. So you wanted to have a good action, and your current policy is already doing better than the old policy for this good action, right? It's generating a good action with higher probability. So in some sense, this is kind of like a great case. And the question is whether you need to reinforce it. Should you still try to take the gradient here to reinforce, to make the probability higher? And PPO's position is that for this case, we don't need to reinforce anymore. So in PPO, the idea is that no need to reinforce. Because it's already a good action, and I'm doing better than the old policy, so I don't have to reinforce. So in this case, in PPO's case, you're going to zero it out. So basically, you just truncate it to make it 0. So basically, you drop this term in this case. If RT is much bigger than 1. Actually, technically speaking, RT is bigger than 1 plus some epsilon. It's called epsilon high. It's a hyperparameter. Sometimes this is like 0.2 or 0.28, something like that. So basically, if RT is already larger than 1.28, then you say, I don't care anymore because I'm already in the right direction. I don't want to risk the instability to, or some kind of instability to keep updating it. So in PPO, so there's also a case when A hat is big, and RT, let's say, is small. Let's say smaller than 1. Okay, there are actually many cases, but let's say you're smaller than epsilon high, right? Something like this. And then in this case, or maybe for simplicity, let's say this is smaller than 0.5. Suppose let's do this case. If you do this case, it means that your current, so this is a good action, but your current policy is doing not as good as the old policy. So that's why you have to increase the policy. You have to increase the probability of the policy to generate AT, right? So you do need to do some work. So basically, that's why you take the gradient. You take the gradient of this thing. So you apply the gradient. Apply the gradient of this surrogate loss. Let's say maybe call this JPPO. So you apply this JPPO with respect to theta, or maybe in some sense, for this particular action, you just basically apply nabla theta pi theta ATST. You apply this, and you do it in the positive direction, so you are trying to maximize the chance. You want to try to increase the probability of this. So as usual, right? So, and actually, in the PPO situation, just as long as it's less than this, you say, good, I'm gonna take the gradient. But in this case, I just drop it. So, and then there's a negative case, which is a little bit different. So in the negative case, there are still two cases, right? One case is that your RT is, say, less than 1 minus epsilon low. And epsilon low is also something like 0.2 in many cases. So basically, if your RT is already small, and this is a bad action. So it's a bad action, and you are generating this action with less chance than the old policy. So you are already doing the right direction. You are already going in the right direction. So, and in this case, PPO will say, no need to update. So this part is also zero out. So you don't have any gradient. And then for the case where RT is bigger than 1 minus epsilon low, just as usual, you update the gradient. Because this is the case when the action is bad action, but you are, in some sense, your probability is not small enough. So if it's a bad action, you want pi theta to be smaller than this, right? You want this ratio to be very small, but you are not small enough, so that's why you should reinforce it to make it even smaller. So, and this is the case study. And if you look at the papers, the formula is actually pretty interesting. So the formula is this. That's often what people often get confused. So they define this kind of like so-called cost function or the reward function, which is this mean of this RT times A hat times this clip 1 minus epsilon high, low, 1 plus epsilon high, RT times A hat. So this is the formula you're going to see in the papers. And it's actually doing exactly the same thing here. So let me try to unpack it. So if A hat is bigger than 0, then all of these terms are positive. And then it depends on which regime you are at about this RT. So if A hat is bigger than 0, if RT is, say, bigger than 1 plus epsilon high, then you are taking this part, right? Because this part is big, because RT is big, right? Let's say RT is 10. This is 10 times A hat. And this is only 1 plus epsilon high times A hat, right? So basically, then the value will be from this part, so it's 1 plus epsilon high times A hat. And because this is a constant, there's no gradient, right? Because this part has no, this clipping thing doesn't have any gradient. If you clip, it's not a variable of the theta, so there's no gradient. And if RT is less than 1 plus epsilon high, then you are in this branch. So this branching will becomes RT times A hat. So that's why it's just a normal gradient. You are applying this gradient. I guess you also need to apply A hat. So you're applying the normal gradient to try to encourage this to be higher. And the same thing for the negative side. If you do the case study, it's actually the reverse, the opposite. So in the negative side, I guess if you check it, it's doing the same thing here. So that's why the clean formula is this, but it's actually just the 4 cases.
Are you saying that the second value is going to be super high? So that the second value is going to be super high?
No, this is not high. This is bigger, right? Because RT is big. I say RT is 10, let's say. So this is 10 times A height. This is only 1 plus epsilon A height.
Yeah.
So that's why you take the mean part.
Right. So in the second case, why wouldn't the RT then? In the second case? Like,
in the second case?
Yeah, right.
In the second case, you are taking this side, right? Because this side is smaller.
Yeah, that's what I'm trying to happen. So the other side is bigger.
You know, in the first case, this is in the first case, this is bigger, right? In the second case,
then why is that bigger? In the second case, yeah, that's what I'm trying to understand.
In the second case, why this is bigger?
Yeah.
That's because take some value. So let's say RT is like 0.5.
Okay.
Then this is clipped to be 1 minus epsilon, say 0.8. So this is 0.5. So this is smaller. This is bigger. Does it make sense?
Yeah.
And if RT is between these two, then these two quantities are the same actually.
So they are dealing only when the new policy is doing that.
You are only yes, or maybe not, or doing yes. So basically, you maybe not exactly because there's some buffer here. It's not like it has to be. So basically, if your new policy is already doing great, you don't update. Yes, and only if the new policy is not doing great, it's not doing great means like it's not much better than the old policy. You are updating. So in some sense, it's kind of like I think the original motivation was that this led you to not move too far away from the original the pi old, so that you can stay in the neighborhood, so that your approximation here, like this approximation that you change this to pi old, is kind of still makes sense. I don't know whether that's exactly the reason, but that's the story. So like you don't want to over update if you are already doing something okay. So yeah.
But won't it mean the learning is slower now?
Exactly. So the learning is slow down. Yes. Maybe let me take it. I think I have actually some response to your question as well, but let me take that question first.
In practice, would we set epsilon high and epsilon low to look different?
Yeah, I think there are papers that try to set them at different values, and actually the magic number is 0.2, 0.28 or something like that. And some people claim that you should do the epsilon high can be a little higher. So And I think one of the reasons is that I don't really expect you to understand this. I don't understand fundamentally, but you can argue that on the higher on this side is probably less of an issue if you don't clip so aggressively. As you mentioned, like if you clip, you are slowing down your learning. You are just making your update smaller because you are already doing okay. And it's kind of like it's probably not a big deal. Like if you're less demanding in this restriction, right? You say, even I'm 2x bit better than the original policy, the old policy, I'm still learning. That's probably fine. So that's why people are more willing to change the epsilon high. In the other side, it's a little bit more about diversity because in some sense, if you are already, so in this case, where you, in this row, right? This is the row that is on the other side. So this is saying that I'm already doing better than the original policy, but this is a bad example, bad action, so I want to minimize the chance, right? So, but sometimes minimize the chance too much has unexpected consequences. You lose the diversity, right? You just penalize this action too much, and somehow like you become too deterministic, and you converge to a local minimum, right? So in some sense, there's you can argue that even the action is bad, you don't really want to penalize it too much. You still leave some chance for it. You give it some benefit of doubt. maybe this action is bad, but combined with some other actions is better at some point. So you give it some benefit of doubt. So that's why on this side, I think there's probably arguably there's more reason to not update, to not overlearn too much. But okay, so now there's a new algorithm called CISPO, which is actually a pretty popular algorithm. Like in my lab, when we are doing the training, we mostly use it as opposed to the PPO. And the CISPO is doing something quite, okay, let me see where should I write it. So let's say CISPO. So CISPO, again, I don't know whether this is fundamentally the right algorithm. It's just what is popular and it's probably the best option. So CISPO is doing something quite different. So if A hat is bigger than 0 and RT is bigger than 1 plus epsilon high, I think maybe it's useful to draw something here. So this is A hat is bigger than 0. And this is, if you do nothing, if you just keep the business as usual, is this line, right? It's RT, the switch line. And GRPO is trying to say, if I'm above 1 plus, let's say this is 1 plus epsilon high, let's say 1.2. GRPO is saying like, I'm going to take 0 afterwards. I have no learning if I'm already okay. So that's GRPO. Sorry, not GRPO, like that's the PPO. GRPO is an advanced version of PPO, which is doing the same thing in this aspect. So this is PPO. And the CISPO is saying that if I'm above 1 plus epsilon, I don't want to disable all the learning at all. I change it to constant here. So that this part is the same, and this part is 1. So you in some sense you clip the value, but you don't you don't drop it. You still keep some kind of like gradient in some sense. Yeah. So so basically you still have some learning, but it's just the learning is not as aggressive as before, right? Comparing to this linear line. And so that's one change. And then the second change, I guess probably I should just visualize it, right? So on the other side, so when A hat is less than 0, so what is PPO? PPO is saying like if it's less than 1 minus epsilon low, I'm going to zero it out, no gradient whatsoever. And after that, I'm going to take linear, right? The standard thing. This is PPO. And CISPO is saying that CISPO is doing something very different. CISPO is saying that I'm going to do exactly the same thing on the positive side. So CISPO is like if you are above 1 epsilon high, you take 1, and then on this side you do this thing. So why this makes sense? So CISPO is saying that, okay, recall that this is a negative advantage case, which means that your action is bad. Your action is not good. So it's saying like in this regime, if you are already smaller probability than the original policy, you're still trying to learn to keep making it smaller. So in some sense, you lose diversity. And actually, empirically, in some of my projects, I do see PPO, CISPO, this new algorithm, CISPO, does lead to sometimes losing diversity. And on this side, is saying that why you are clipping here. Right? The reason is the following. The CISPO's reason is that anything that makes any case when the R is big is a bad case. Because if R is big, then the gradient is also big. So you just, if R is big, then sometimes you have too much weighting here. And you have too much instability. So like this term contributes to the gradient too much in some sense. Like if not because whether you have learned or not, whether you have like done good or bad compared to the old one. It's just because the update is too big. So basically the CISPO's philosophy is that just because I don't want to have big update, I just clip anything that is big. Especially sometimes this ratio can be very big because this is a probabilities, right? It could be like this is 0.2, this is like 0.6. And then you have a ratio of 3, or maybe this is 0.01, this is 0.6, and you have a ratio of like 60. So basically I just don't want to have big terms in this, in this equation. Again, I don't know whether that's really right or not. That's what's argued in some of these papers. And then, every few months, there's a different clipping. I think there's another paper which actually does some combination of the CISPO and PPO by clipping a slightly different way, so on and so forth. Anyway, so I guess probably we should just stop here about about this topic because it's still open research area. So we don't really know what's the true answer. Okay, any questions before I move on to? Okay, so I only have 20 minutes, so I need to talk about, I want to talk about how to apply this large language model. I think the way to apply it is, so to talk about that, I think the first thing to discuss is that there is a notion of like chain of thought. And it's actually very simple. So in our, all of our per discussions, right, we have some prompt x1 up to xt, let's say. Maybe L. So this is your question, let's say. Let's say, suppose the question is, what is 1 plus 1, right? And then you ask the model to generate y1 up to yk. And this is your answer, right? So basically, you ask the question, the model will generate the answer right away. And then people realize that actually letting the model to generate answer right away is not necessarily the best thing. You probably should let the model to think for a little bit and then generate the answer. So the chain of thought is like this. You send some kind of like prompt, some question, and then you let the rest of the things is all generated by models, but this model will generate some thinking tokens, right? And maybe and then generate the answer. And often the thinking tokens start with this some special thing called this special token like this, and then you end it with a special token like this. It's not always the case. Sometimes the models don't even generate these tokens. They just keep thinking. Actually, I think the Quinn and the DeepSeek models just don't even have this kind of like special segmentation. You just generate the thinking right away, and then you generate an answer. And the how this was discovered, why this was useful at the first place. It was first discovered in this context of solving some of the math questions or some of the questions that require steps. For example, the question could be like can you it's kind of like a math question, and then you have to do a few steps and then get the answer. You cannot just directly, no human can actually get the answer right away because it does require some steps, right? So then this Z1 up to Zn is actually laying out those kind of like calculations, right? Step-by-step calculation. And in the first paper, what people do is that people are using few-shot learning to encourage this kind of like behaviors. So basically, you give I think we discussed few-shot learning, which is kind of like you give the models a few examples on how to solve the problem, and then you let the models to follow the example. So in the examples, you give a few of this kind of like handcrafted few-shot examples. You say, like, I want you to solve this question, right? But before letting to solve the question, I first give you 3 similar questions and tell you how to solve step by step and give you the thinking process and then give you the answer. I have 3 such examples, which all look like this, and you concatenate them all in the prompt, and then you say, now solve the question, my new question, following the same process. So that's called few-shot COT. So I think that's initially how it's discovered. And then later on, So this few-shot COT. And then later on, people also found out this kind of zero-shot COT. And what does zero-shot COT means is it's actually much simpler. It just means that in the prompt, you don't give all the examples. You just have a question, x1 up to x. You have a question. And then you add in your prompt, please think maybe there's no please think step by step. Or let's think step by step. And this is part of your prompt. And then you let the models generate the answer. And because you add this, then the model will naturally start to think step by step and then give you answer. And just basically these few magical words will make your accuracy improved by like 5-10%, or maybe even sometimes 20%, even more. So that's the so-called zero-shot COT. And then later, people figure out that, if this is so useful, why don't I try to reinforce? Why don't I try to train the model to have stronger capability like this? Why don't I do something like training so that this kind of capability is more kind of like prominent, right? So then that comes to like, how do you train the models to have these kind of behaviors, right? You can try to have a lot of like, I think the first kind of like a set of idea was that you try to do some instruction tuning. Basically, you create a data set with these kind of like behaviors, and then you manually create data sets with this synchronous step-by-step thinking, and then you train the models with the supervised fine-tuning. But that's limited because in some sense you don't really know what's the best way to think step by step, right? Like the human thinking. Actually, if you look at the step-by-step kind of like thinking, like the thinking tokens of any of these open source models, you take, because the closed source models, you don't even see the thinking tokens. You only see some summary of how it's thinking, right? If you look at the open source models, you look at the thinking tokens, it's actually not very logical, right? There's a lot of like back and forth, sometimes it's using kind of like very succinct shorthand and sometimes it's kind of like skeptical about the question, it's not a very coherent, clear, shortest thinking path. It's actually a pretty lengthy back and forth, which is kind of probably similar to how people solve questions, right? You try different ideas, you reflect on what you have done, all of this, right? So that's why if you try to handcraft the thinking process, sometimes you don't even know how to generate those kind of messy thinking process. Actually there was a study on this, like people try to generate very, very succinct thinking process, but those succinct thinking process actually are not very useful for the model because it's just too hard to think that way. You have to spend more time and thinking in a less logical way in some sense. So that's why this kind of like a supervised approach is hard. It does work to some degree, but it's kind of like hard to scale more and more eventually. So that's why people found out like we can use reinforcement learning to train the model. So the benefit of reinforcement learning is that you don't have to have the labels on how to answer the question. You just have to judge whether the answer is correct. So basically the idea is that you view this, so using RL, you view this whole generation process as a, so basically you take in this and you give a reward. So you give a reward of the whole trajectory, right? So this X, So you reward the whole trajectory, but only based on answer. So you reward the trajectory based on the final answer, y1 up to yn. You don't really care about how the thinking was done. You just care about the final answer is right. No matter how you think about it, as long as you are doing the right thing, I'm fine with whatever thinking you want. So as long as I can verify the answer. So maybe formally, what it does is that so you view this kind of like a large language model generation as a MDP, and you assign a reward and you apply the reinforcement learning tool. So basically, the way to do it is that let's say large language model, and this is the RL world or the MDP world. So I think let's see. So maybe we don't even have to distinguish the thinking versus the, so let's say in the LM you have some input x1 up to xl, y1 and some generation y1 up to y, say n, and some part of this is answer, some part of this is thinking. For this discussion, maybe let's don't even distinguish them. And then what you do is you say the MDP, the state of the MDP. So like, how do I say this? So the state ST corresponds to all the previous generation. Actually, let me just try to use my notes so that I don't use the wrong symbol. So the state is both X and all the previous generation. And the action is just the next generating token. It's my action. So the action AT is corresponding to the YT. And what's the transition dynamics? So recall that in MDP, given a state, given action, you need to predict what is the next state. And the transition dynamics is given ST and AT, right? So you need to give both of these two to predict what's ST plus 1, right? Right. So the ST plus 1 is actually trivial because the ST plus 1 is just a concatenation of these two. So ST plus 1 is just so if you, let's see, suppose you use this to get ST plus 1. ST plus 1 is just literally X, Y1 up to YT minus 1, and then concatenate with YT. So the dynamics is actually completely deterministic and trivial. But still, it's very hard to control this dynamics because you are applying actions every time. It's a long sequences, right? You have to generate the right tokens in a sequence. Eventually, you can get the answer. And then the reward, so the reward function, in reinforcement learning is applying for every state and action pair. So here, the reward function is only applied at the very, very end. So the reward is only a reward of the whole trajectory. So you just only care about the reward of the whole trajectory, which is the final state, right? So the whole trajectory y1 up to say yn, and we give this as a reward. And the reward is really literally just whether the answer part, let's say this part is the answer. So whether answer match the ground truth answer. So so it requires that for this data set, you do know what the ground truth answer is. So for example, it's a mathematical calculation problem, then you know what is the resulting calculation, the final result. And you can see whether the result you get matches the result that the ground truth result is. So that is a reward. And the reward is often binary. So I guess I'm running low in time a little bit. So the reward is often just the reward is just 1 if matching, and 0 otherwise. Of course, in reality, there's a lot of variance. For example, you also have to consider whether the formatting is right. For example, whether you can extract an answer from this quickly. You cannot use another AI model to extract answer. You have to extract answer in a very pragmatic way. So actually, in reality, what happens is that you try to ask a model to generate the answer enclosed by a tag. So you say bracket answer and the answer, and then like with this kind of like XML kind of tags like this thing. So you say this thing has to be within answer, and then answer something like this. And then you use a parser to extract what was inside, and you match this with the ground truth answer, and if it's matched, then you have 1, otherwise you have 0. But of course, these days I think the models are better and better, so you can ask the model to generate different kind of like formatting now. But at the beginning, it's just a formatting kind of like this very simple way. Yeah, so that's the. And then you can apply the PPO algorithm. You can apply the SysPO algorithm with this formulation. So eventually, the algorithm, if you apply all of them, then you will get something like. Maybe let me just. I think my. So eventually the algorithm looks like. well, it could be very complicated, but like something like you, for example, you can have something like the RT. In this case, the RT is the ratio of the two, the actions, right? So, but in our case, the RT will be something like, recall that the action is the next token. The ST is the history. So the RT just becomes the pi theta yt given x and y less than t, and divided by pi theta old yt given x and y less than t, something like this. So, and then you apply this with all of those advantage functions, and you just plug in the same algorithm. And there are a lot of other details which I think is probably, I try to mention them, some of them in the lecture notes, but again, I guess some of the details are not quite well understood. So you can try to, for example, add some regularization so that you don't deviate from some reference policy too much. I think that was very useful at the beginning. Now, whether it's useful or not, I don't really know. So, and you can also, one important thing is you can, how do you design this baseline? So the baseline BST, I've never discussed too much about how to design the baseline. So in the old days, you actually learn a value function, you learn some neural networks to estimate the baseline. But a new way to do it is that you just sample, say, 8 trajectories, and you take the average. So you can say from the same question, so I mean large language model world, so you have a question, and you sample 8 trajectories. Here I'm using the superscript to decide different trajectories. And each of the trajectories has a different reward, right? So each of these structure has a reward R1 up to R8. And then you average them. Let's call it R bar. You do average. And recall that this average, in some sense, is only a function of the question X, right? Because it doesn't really, because you average it, right? It's not about any specific, it's a statistic about the how hard the questions are in some sense at this moment, right? And this will be your baseline. So basically what happens is that suppose you have a bunch of like a reward, and maybe let's say one of them is 1 and all the others are 0, and your R bar will be 1/8. So basically you subtract 1 over 8 from 1, and that's your adjusted reward, and all of the other ones have minus 1/8 as reward. So, but if you have a different situation, let's say suppose you have 5, so basically in this case, I guess this will be adjusted to 7/8 minus 1/8. Okay, I guess so you will adjust the 1, 0, 0, 0, 0 to 7/8 minus 1/8 minus 1/8. But on the other hand, suppose you have, for example, 1, 1, 1, 1, and 0, 0, 0, 0. You have 4 1s and 4 0s. Then they will be adjusted to 0.5, 0.5, 0.5, 0.5, minus 0.5, minus 0.5. So that's the adjustment you do. And there are actually other ways to adjust it even further. You can divide by standard deviation as well, so that you can scale up a little bit. But maybe let's leave those for future offline reading. Okay, I guess I probably should stop. Any questions?
The space is too long. I don't know why models find the right trajectory. Because without the supervision, how to find the right thinking?
So basically, the space is so complex, right? Yeah. So one thing that is very important is that you have to start with some policy that can give you a non-zero reward. So you have to have an initialization that give you some positive reward. And actually this was interesting. So you probably know Llama 4, you have heard of it, right? So one of the problems with Llama's model is that they have no thinking capability whatsoever to some degree. I'm maybe exaggerating a little bit, but just they have very, very limited thinking. They almost have no thinking capability, so that when you use RL on them, you have 0 rewards at the beginning, and you just keep having 0 reward in some sense. But some of the other models, like Quinn or DeepSeek models, if you start, you already have some thinking capability, like very little thinking capability. But once you have one successful trajectory, let's say it's like this, 1, 0, 0, 0, and then you will reinforce this trajectory with 7 over 8, and you penalize all the other trajectories, right? So then you kind of start to see this behavior gradually, and then you keep bootstrapping in some sense. So getting non-negative reward or getting some reward is very important. And how people get the reward, sometimes you try to do some SFDs to start with. So you first kind of like we discussed, you create some data so that the data has some kind of thinking process. Maybe even you try to make the data, you try to inject some reflection in the data, say, oh, you try to have a messy, long thinking process and say, oh, I checked my answer before and I reflect a little bit and I correct myself in the thinking process. And then you probably get this behavior a little bit, and then you can use the RL to bootstrap. I don't know all the other approach in the frontier labs on how to get a non-zero reward, but it's pretty important to get non-zero reward. Yeah, or sometimes the pre-training data does have something like this, right? So like some of the pre-training data actually has this kind of thinking process in a very kind of like lengthy way. So you probably get some of those from there as well. The reward is always assigned in a very pragmatic way, right? Like you have a ground truth answer and you just use a program to match it's very, very simple program to match the answer. Of course, these days, so for some of these cases, you don't have ground truth answer, then people are also trying to use a large language model as the reward function. So you can extract the answer and then just directly evaluate the answer, whether the answer is correct or not. I think there's always a risk that the large language model's evaluation of the answer is kind of like hackable. So basically, they are not checking really the answer is right, but they are just checking the format, checking the style of the answer, and then if the model, the solver, right, the model that generates the answer can hack it in some sense. Exactly how much degree that can be done, is still an open question, because if you use all the 4B model, then of course you can hack the reward function. But if you use maybe a gigantic kind of like model as the reward function, can you hack it or not? I think that's still not entirely clear.
One more question about so like in the normal large learning model, like the normal neural network, we have this big compute requirement. In this, I'm trying to understand if the compute requirement is going to be, what exactly is going to determine the compute requirement? Because is that the policy like is going to determine like the pi of theta, like how much compute you need? I didn't see like any compute kind of part in this.
Yeah, because it's already a little bit complicated, so I didn't talk too much about it. So you have two phases where you generate the trajectory, and then you assign a reward, and then you take the gradient descent step, right? Compute the gradient, you take gradient descent, right? So basically, there is a generation phase, there is a rewarding phase, or evaluation phase, and I think it's called reward phase calculation, and then there is a training phase. So the training, it depends on the scale and how long your generations are, right? So typically generation is slower than the training, I think, because for generation you cannot really parallelize. You have to generate token by token. So and the training it's kind of like you are just fitting the whole. It's pre-fitting when you do training. You already have the trajectory. You are just computing the forward path. So I think typically the generation is slower than the training. Yeah, and the longer the generation is, the slower it is, because you have to keep all the KV cache in the memory.
And the generation is like a pre-trained LLM. I mean, yeah, we don't. Yeah, I think that.
And this is different from pre-training, because in the pre-training there's no generation phase. All the trajectories all the data you have are downloaded from the internet or pre-processed, so on and so forth, right? So you are only doing the training but no generation. But here you have the generation phase. Sounds good? Thanks. Yeah, thanks for the culture.